in this direction and it is continuously trying to drift the plane in this direction. Slight miscalculation and the plane will be deviated so much that it will find jungle all around it. If the pilot starts steering the plane due north, then it will be drifted by the wind and it will start going in this direction. Okay, but this is not permitted. So the pilot will have to do something such that it can neutralize not the wind as a whole, but the detrimental component of the speed of wind. Because the speed of wind as a whole is not disturbing. You can find a component of the speed of wind which is actually helping the plane. So we do not have any confrontation with that particular component. We will try to neutralize the component of wind speed which is disturbing the plane. So first of all, we have to understand which component is disturbing the Earth is a reservoir of charge. It can supply any amount of charge. But on demand, this is very vital. If there is a demand for the charge, then only it will supply. And it will not supply any surplus amount or any deficit. It will supply the exact amount. It is a reservoir of charge. Okay, like you consider your papa as a reservoir of money. Okay, but he will supply, he will give you just the exact amount. Means just to meet the demand. Okay, so now this is plus Q inside, and you have to do the charge distribution. Now first thing that you will consider whether this is conducting or not. Since this is conducting, field inside the material. Field inside the material is 0. So what is the total flux through this?
0.
It is 0. So what should be the total charge inside?
Minus Q.
Total charge inside should be
0.
0. But already there is charge plus Q. So minus Q charge must appear on the inner surface. Now this time Earth will supply. Not idhar ka mal udhar. Not like that. Previously idhar ka mal udhar. Because the outer shell was not connected to any source of charge. So that's why there was adjustment in that case. But in this case there will not be any adjustment. Because this body is connected to the source of charge. And there is a demand for minus Q. So Earth will deliver minus Q. So what will be the difference in charge distribution? On the outer surface, there will not be any flux. In order to understand the circuit, split intermediate plates to form an H. Battery potential will be given to you. Suppose this battery potential is 6 volt. Find the charge delivered to each plate. So what we'll do, we'll split the intermediate plates to get an H. Then I have connected these two plates. You can see I have connected these two plates with a conducting wire. Because this is single plate, so it has a unique potential. So that's why these two parts also must have same potential. To ensure that they get same potential, they remain at same potential, I have connected these two with a conducting wire. Okay, so I have split the plate in. So this becomes N1, this is N2. Similarly, I will split O. I will get O1 and O2. And I will redraw the circuit to get a simple combination. Okay, so A, I am not splitting A, then N1, N2, N1, N2 A, then O1 O2, then P, not splitting P, side plates, I will not split side plates, I will split only the intermediate ones. Now I will give connection. To get a better understanding of the connection, I will give this connection to the side. You can see the where is touching the top. In order to get an easy to understand view, I will take the connection from side. Okay. Then this has gone to O, that means middle of O1 and O2. Okay, it has gone to O, that means middle of O1 and O2. And same will apply to this. The connection, battery connection is given to this point. I will show this. I will take this from side. Then this has gone to N, that means to N1 and N2. I think now the circuit is visible to you. If you enclose the charge using a cylindrical Gaussian surface, then you will get total flux falling on this Gaussian surface. That is quite easy, Q by epsilon naught. Because only charge present inside is Q, so Q by epsilon naught is the total flux falling on the entire Gaussian surface. So falling on the entire Gaussian surface is Q by epsilon, that is known. But how much of that is falling on this surface? How will you find that? So this situation is different. This situation is different from this situation. In the last class only we solved a problem where in this particular problem we have a charge kept at the center. Charge is kept at the center. The bulb is hanging exactly at the middle of the room. If the bulb hangs exactly at the middle of the room, then all the surfaces will receive same amount of flux. So it is easy to find the flux falling on one surface, Q by epsilon naught by 6. But consider the same problem. If I tell you that the charge is placed here, not at the center, and if I ask you how much flux is falling on the bottom surface, it will not be easy at all. Because total flux is known, Q by epsilon naught. But this surface, which is closer to the charge, see the top surface, top one, it is closer to the charge, so it will receive more flux compared to this surface which is away from the charge. So you cannot divide the charge. You cannot do Q by epsilon naught by 6. Here also you cannot do Q by epsilon naught by 3 or Q by epsilon naught by 4. Total is known, but how much is falling on this surface is not known. How much is falling on the curved surface is not known. How will you find? We'll use what is known as solid angle. Solid angle. It is different from a plane angle, and you can see some type of angle here. Okay, that means suppose I have placed a bulb at this corner, then amount of light coming out through this conical thing, or I have kept a source of sound here, a small micro speaker. How much sound energy is coming out in this direction? So we will now solve this problem by using the concept of solid angle. This is emitting I have told you that you may compare, you may visualize all these as an amount of light coming out from a tiny bulb. And the question that you have been asked is, how much of the light is falling on this surface? So, before you calculate the light falling on this surface or the flux falling on this surface, you should know the total flux which is coming out from this. Total flux is known Q by epsilon naught. And what is the total solid angle around that point? This is a point. What is the total solid angle around that point? 4 pi. So 4 pi solid angle corresponds to how much flux? Q by epsilon naught. And your job is to, now your job is to calculate the solid angle separated by this surface. Find this solid angle. I think you have understood how to solve the problem. Just calculate the solid angle separated by this. Then you know, for 4 pi solid angle, amount of flux is Q by epsilon naught. For this much solid angle, amount of flux is this. In books you will find there are a lot of rules. All those rules are actually based on a single concept. A single concept. If you know that concept, then you are not required to remember all those rules. And that simple concept is, by changing unit, you cannot change the number of significant figures. Significant figures gets fixed. Significant figure in a measured value. You have measured something. Significant figure in a measured value gets fixed as soon as the measurement is done. Thereafter, you cannot change the significant figure in a measured value. Okay, I am explaining this. This is the basic concept. Length of a rod, it has come out to be, say, 2 meter 32 centimeter. Okay, so this is 2.32 meter. Of these 3 digits, 2 is known to be correct, known with certainty, 3 is also known with certainty, but this one is uncertain. Okay, so this measured value has 3 significant figures in it. Okay, 2, 3 are certainly known and 2 are uncertain, first uncertain digit. Okay, so number of significant figure in this is 3. Okay, and what I have told you, that significant figure gets fixed as soon as the measurement is done. This is your measurement, significant figure is 3, and thereafter it will never change. How it can change? Thereafter it will never change. This is measured value and SF in this equal to 3. Okay, then suppose you want to express it in millimeter. Okay, your experiment is such that this has to be expressed, this has to be written in millimeter. So length L equal to 2320 millimeter. Okay, how many significant figures do you have in this? 3. Because once it has been fixed, once the measurement is done, thereafter it will never change. It will never change. This may be stated in form of a rule. You will find this rule in book. But if you know the basic fact, you are not required to remember all these rules. You will find several rules. One such rule states that zeros coming up after some non-zero digits are not significant. Both stationary. Finally, the kid has started moving at 2 meters per second. Okay, at 2 meters per second. Question is, at what speed will the trolley move? Now, what is this 2 meters per second? 2 meters per second is the normal speed at which the kid can walk. Try to understand this point. It's a very important point. Okay, there is much in this statement that 2 meter per second is the normal speed that the kid can walk. That means when the kid walks on road, he walks at 2 meter per second only. Okay, so 2 meter per second is the initial, then 2 meter per second, and this is going, this will go backward in order to keep the total momentum conserved. What is the initial momentum? 0. And by walking, the kid has gained some momentum. In order to make the total momentum 0, the trolley has to move backward. Suppose with a speed v. Okay, so what is the initial momentum? 20 into 0 plus 100 into 0. Total equal to 0. This is the total moment, total initial momentum. Finally, what is the momentum of the kid? What is the momentum of the kid? In such case, whenever you apply conservation of momentum, this is very important point, all the velocities must be taken with respect to ground. All the velocities must be with respect to ground. 2 meter per second is the speed of the boy. I have explained. When he walks at 2 meter per second. So on the platform also he is walking at 2 meter per second. So this is the speed with respect to the trolley. What is the speed with respect to the ground? It is 2 minus v. With respect to ground means, with respect to someone who is located on the road, standing on the road. With respect to the trolley, he is walking at 2 meter per second. But in the same time, the trolley is moving backward. So what is his speed with respect to ground? Simple example, suppose you are on a trolley and you have taken 3 steps in 1 second. 3 steps in 1 second. In that 1 second, the trolley has gone backward. It is fitted with wheel. So the trolley has gone backward by 1 step. So you have taken 3 steps on the trolley, but in that time trolley has gone backward by 1 step. So with respect to ground or with respect to this board, you have gone forward only by 2 steps. That is your speed with respect to ground. And in conservation of momentum, always you have to use velocities with respect to ground. Finally, 20 into this 2 meter per second is obviously with respect to trolley. If you put 2 here, then you are utterly wrong. Reason is 2 meter per second is the speed with respect to trolley, and by convention means by guideline, always you have to use the velocities that are with respect to ground. So with respect to ground, the speed of the kid is 2 minus v plus momentum of the trolley, which is 100, and be very careful about sign because momentum is a vector quantity. So 100 is negative momentum minus v equal to this is final. Then since F external, will you write F external equal to 0 or will you write F external in horizontal direction equal to 0? Since F external in horizontal direction equal to 0, hence momentum will remain conserved in horizontal direction. Hence momentum will remain conserved in horizontal direction. Okay, so now total initial momentum 0, total final momentum 20 into 2 minus v minus 100v or
complex topic discussed in most simple way. To buy, call 94340 or SMS or email.
So mind it, total momentum in vertical direction just before explosion is equal to total momentum in vertical direction just after explosion. But total momentum in vertical direction 1 second before explosion is not equal to total momentum in vertical direction 1 second after explosion. Simple reason is during that 1 second or 2 seconds, external force will act on the system. Okay, have you got this point? Two bodies are colliding, very valid point. Two bodies are colliding. Now this is your U1, this is U2, and in vertical direction U1, U2, and after collision they have moved apart. Then velocity of one body V1, velocity of the other body V2. Can you use these velocities? Because see, there is a distance, so they will, for coming in contact, they will take some time. During that time, external force will act and momentum will not remain. But what if you take the velocities just before and just after? Just before collision U1, U2, just after collision V1, V2. Then external force is not getting time in which it can act on the system. Okay, is it clear? So if there is external force, use the velocities just before, just after. When there is no external force, you can use the velocities 1 year before, 1 year after. No problem. Current is entering at the point A and current is leaving at the point B. This is also a three-dimensional circuit. We will have to convert it into a two-dimensional one in order to find its equivalent resistance. For that, we will take the help of a plane mirror. The plane mirror should be such, as I have already told you, the plane mirror should be such that it contains the point at which the current is entering and the point at which the current is leaving. These 2 points in its plane, and it should also divide the whole volume of the circuit. In the case of three-dimensional circuit, whole volume of the circuit, and in the case of two-dimensional circuit, the area of the circuit into 2 equal halves. Okay, so I'll show the mirror here. It must contain the points at which current is entering and current is leaving. So first we draw this line, then we draw a surface which will divide the whole volume into 2 identical halves. So this is the surface of the mirror. This is the surface of the mirror. So you can see that it has divided the whole volume into 2 identical halves, and it also contains the point at which current is entering and the point at which current is leaving in its plane. What is the advantage of, or what is the use of this type of mirror? When you use a mirror, there you will find points which are object image pair. For example, this particular point, if you consider this to be object, then this is the image. That means, let us name it A, B, C, D, E, F, G, H. So points F and H are object image pair. F, H. Since F and H are object image pair, hence they have same potential, and since it is an electrical circuit, points having same potential are treated as same points, so we will connect F and H, means we will paste these 2 points F and H. So F and H. Similarly, D and C, if you consider D as the object or C as the object, if you consider C as the object, then D is its image. So D and C are 2 such points, object image pair. So you can paste these 2 points together. Okay, so now I'll redraw the circuit. Altogether there are how many? 4 plus 4, 12, 4 plus 4, 8 and 4, 12 resistors. So I will be drawing all these resistors. So I have drawn between E and F, that means this has been drawn, E and H, this also has been drawn, F and G, this has been drawn, H and G, this has been drawn. That means drawing of the upper surface is finished. Now I will draw the lower surface between A and C, between A and D, between D and B, and between C and B. Okay, so drawing of the or conversion of the lower surface is finished. Now I will draw the resistors along the vertical edges of this cube. E and A, G and B, F and D, F and D, H and C. So let us count. 4 plus 4, 8, 9, 10, 11, 12. So that means we have finished drawing of all the 12 resistors, and what we have got is a two-dimensional figure, two-dimensional circuit. So these two. So now we can calculate the equivalent resistor. These two are in parallel, 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 these two are in parallel. Two forces are acting on the bob, T and mg. Okay. I have resolved mg into two components. One is along tangent, other one is along the radius. Mg cos theta and mg sin theta. Now along the string, means along the radius, we find that there are two forces. One is T and the other one is mg cos theta. Are they equal, T and mg cos theta? How are they related? Is T equal to mg cos theta? Or is mg cos theta greater than T? Or is T greater than mg cos theta? T is 5 Newton and mg cos theta is 4 Newton. Is this situation possible in this direction? Or should it be like this? 4 Newton, 5 Newton, or 4 Newton, 4 Newton.
5 Newton, 4 Newton.
5 Newton, 4 Newton. That means the direction, there is a resultant force in which direction?
And
towards the center. And that net force towards the center is actually centripetal force. You got the point? There has to be a net force towards center or not? In absence of that force, no particle would go along a circle. Now this bob is going along a circle, so there has to be a net force towards center. So should it be, if this is 4 and 4, both are 4, what is the net force towards center? 0. Particle will not rotate. If this is 5, this is 4, then also there is no net force towards center. Particle will not rotate. Only in such case there is a net force towards center. And that net force, that means 5 minus 4, as per this example, is the centripetal force. Now net force towards center equal to, what is the net force towards center?
T minus MG cos theta.
And this is what? This is actually the centripetal force. Net force towards center is T minus mg cos theta. Hence, T minus mg cos theta equal to centripetal force mv square by r. It basically states that high velocity, whether liquid is flowing with greater velocity or some air is flowing with greater velocity, high velocity is always associated with reduced pressure. High velocity is associated with reduced pressure. Consider water jet. Surrounding this water jet, the pressure is PA, atmospheric pressure. Pressure is PA, atmospheric pressure. But inside the water jet, the pressure is less. Okay, here the pressure inside is smaller. It is smaller. This will produce a air jet. And if you place the ball above this air jet, what will happen? Will it go to the top and hit the wall? Hit the ceiling?
At to minimum
Stay here. And if I till the air jet, it will go. Then will the ball fall?
Yes, sir.
But I have already told you that surrounding the air there is greater pressure, and inside the air jet the pressure has gone down. So even when it is tilted, it should not fall. Okay, for some angle of increase, for some till at least it will remain. It should remain here. Air jet. This is the air jet. Okay, so if I release the ball, then you may be thinking that if you keep it, they don't do that for you. That is because surrounding pressure is greater, and it is pushing the ball away towards the interior. Displacement x equal to a cos omega t or x equal to a sin omega t. See, it all depends on your choice of t equal to 0. T equal to 0. This body is oscillating. This body is oscillating. And you have a stopwatch in your hand. The body is oscillating. You have a stopwatch in your hand. You have not yet started the stopwatch. When the body has reached the end position, you have just started the stopwatch. Then x equal to a cos omega t. Okay? When the body has reached the end position, you have started the stopwatch. X equal to a cos omega t. That means you are measuring time from the end position of the body. X equal to a cos omega t. We are measuring time from the end position of the body. See, I have indicated this position at t equal to 0. Okay? So very clear, wooden block is oscillating. You have a stopwatch in your hand. It has reached the end position, you have started the stopwatch. Then for that motion x equal to a cos omega t. On the other hand, the body is oscillating. You are with the stopwatch. Then it is just passing through the mean position, you have started the stopwatch. When it is passing through the mean position, just at the mean position, passing through the mean position, started the stopwatch. In that case, x equal to a sin omega t. I'll establish it here. Okay. So in this case, x equal to a cos omega t, and now see this one. Okay. This is rotating with uniform angular speed. Okay. And its foot of projection is moving. It is rotating. Then at some instant, this particle, sometimes I will call this particle as parent particle. Okay, because this is actually the parent of foot of projection. So at some instant, the parent particle is here, going in this direction. Going in this direction. Parent particle is here. The foot of projection is here, going in this direction. Okay. Right at this instant, you have started your stopwatch. So that means I will mark this as t equal to 0. Okay. So it all depends on your choice of t equal to 0. Particle has nothing to do. The body is oscillating. It all depends on your choice of t equal to 0. Then at t equal to t, the parent particle has moved to this position. At that instant, the foot of projection, it has, at that instant, the foot of projection is here and going in this direction. Okay? Which angle is omega into t now? This angle, omega into t, because angular speed is omega, omega is uniform. So in t second, what angle will it describe? Omega into t. And displacement is always measured from mean position. There is no change in that convention. This is x. This angle is omega t. Amplitude is a. So how much is x in this case? X equal to a. This is a cos omega t, and x equal to a. The wave is traveling in this direction, and it will get reflected from this rigid wall. Due to reflection from rigid wall, the phase of the reflected wave will instantly increase by pi. Due to reflection from rigid wall, the phase of the reflected wave will increase by pi at the instant of reflection. This is the pulse traveling in this direction, falls on the rigid wall, and since this is a rigid wall, the phase of the reflected wave will instantly increase by pi. Means phase will be opposite. The reflected wave will immediately have a reversal of phase. Okay, have a complete reversal of phase. And you can see this in drawing. This is what is called a complete reversal in phase. Okay, so this is the incident wave falling on a rigid wall. From that, this particular wave rebounds, and you can see the phase of the reflected wave. It has increased by pi. Okay, now you will understand it better if I compare this with reflection from a free wall. Okay, what do you understand by a free wall? A free wall or free end more appropriately. This is a frictionless rod, okay, and this passes through a ring. There is absolutely no friction between the ring and the rod, okay. Then this is a string connected to the ring, and a kid is producing jerk in it. Okay, this end is called a free end. Reason is this ring, between this ring and the rod, there is absolutely no friction. That means the ring can move without any hindrance. It can easily move along the rod. It is not rigid, it is completely free. In such case, here the kid has produced a jerk in the way. This jerk in form of a pulse travels in this direction and it will reflect without any reversal of phase. That means, see the reflection, I am showing the reflection here. No reversal in phase. I have given you two springs. This is one spring. Okay, these two ends are connected. These two ends of the spring are connected by a thread. Okay, and thread is under tension. And there is one more. And I have asked you, what is the difference in the lengths of these two springs? You will not be able to answer. You will tell me what? That first this thread should be cut. Spring should get its normal size. Then we can measure the difference. Isn't it? Because this is free. But these ends are bound with a thread and this in a compressed state. And if someone asks you what is the difference in length, first thing that he will do, he will cut it and it will get its normal length and then he will measure the difference. Consider light. This is glass and light is passing through this, and similarly there is light outside this. If I ask you what is the difference, you see it is AB and it is CD. What is the difference in their length? You will not be able to answer. Because inside this, the light is like this, in bound state. Wavelengths are small, shorter wavelengths, while outside it is like this, free. So what you will tell? First we will make this light free. Okay, so how will you make this free? You will place, if you place this path of light in here, immediately it will elongate. Immediately it will elongate itself, it will be like this. Okay, now this is in here, this is also, this has become, this is also in here, and you can measure their difference. Okay, so this actually it is like this. In once light enters into a medium, the wavelengths get shortened. So or you may think that it is in a squeeze state, and unless you can make it free, you cannot tell the difference. Okay, so when it is made free, its length becomes mu into T. Inside this, in squeeze state, it is T. When it is made free, its length becomes mu into T. And now this length can be compared to this. Because both are free. Due to fission energy is released and due to fusion also energy is released. This fact has to be understood. Why is energy released? Now this element is trying to attain stability. How will it attain stability? Obviously by reducing its mass number. So this AX240, it undergoes fission and it produces two atoms of Y120 and Y120. Okay? 120, 240 and for element with mass number 120, mass number is 120. For this element, the binding energy per nucleon figure is with us. What is the value? How much?
8.5.
8.5. So, how much energy you have to supply to split this? We have already defined binding energy. That is the minimum energy that you have to supply to split an atom, to split a nucleus, and to send all its constituents to infinite separation. So consider X, an atom, a nucleus of X. How much energy will you have to supply? How much? Binding energy per nucleon figure is how much? X, no, for X, for 240 it is 7.6. So how much energy will you have to supply? 7.6 into 240. This is 7.6 MeV is per nucleon. Per nucleon, how many nucleons does it have? 240. So X 240. So 7.6 into 240 MeV. This much energy you have supplied. As a result, what has happened? All the nucleons, they have gone to infinite separation. You have supplied energy, they have gone to infinite separation. Now you are bringing them together in order to form a nucleus of 120. So this time energy will be released. If you find that the released energy is greater than the supplied energy, then there will be a net release of energy. You got my point? First of all, you are doing what? You are supplying energy. Okay? How much energy have you supplied? Obviously you have to supply energy equal to binding energy. Per nucleon it is how much? 7.6. There are 240 nucleons. So this much energy you have supplied. Okay? Now the nucleons have all gone to infinite separation. Now you are condensing. You are bringing these neutrons and protons to form Y. You are bringing these neutrons and protons to form another Y. This time energy will be released. How much energy will be released from this? Its binding energy is 8.5. So 8.5 per nucleon, and it has 120 nucleons in it. Okay, MeV. And this will also, it will emit energy how much? Again 8.5 into 120 MeV. So now we'll do in some net calculation. Energy supplied, energy released. Energy supplied equal to 7.6 into 240 MeV. Energy released equal to energy released equal to 2 into 8.5 into 120 MeV. Hence, there is a net release of energy. Net energy released, this minus this, equal to 240 into 0.9.
Most complex topic discussed in most simple way. To buy, call 94340 or SMS or email. Most complex topic discussed in most simple way. To buy, call 94340 or SMS or email.